Out of a total production run of 129 airframes, no complete example of the Douglas TBD-1 Devastator is currently held by any museum worldwide. The type survives physically only in submerged wrecks and scattered components. That absence from museum collections sets a hard boundary for aviation archaeologists. It elevates any surviving cohesive wreckage from a standard recovery target into a high-stakes forensic retrieval. Bureau number 1515 is a Douglas TBD-1 Devastator assigned to Torpedo Squadron 5, originally attached to the aircraft carrier USS Yorktown. It currently rests submerged at the bottom of a Pacific lagoon. The primary operational objective is to safely extract this structurally cohesive airframe for stabilized museum display without inducing mechanical collapse. The initial constraint governing any military aircraft recovery is the legal and ethical treatment of a potential war grave. If an aircraft contains human remains, disturbance may be prohibited or tightly controlled by protocols designed to protect the site. Bureau number 1515 presents a verified exception to that specific concern. Historical records confirm that all three crew members, the pilot, the bombardier navigator, and the radio man gunner, survived the ditching, evacuated the airframe, and were later captured, spending the remainder of the war as prisoners. No crew remains are therefore expected within the submerged airframe. That fact removes one major ethical concern, but it does not clear the site for unrestricted recovery. The aircraft remains protected military property, and any disturbance still depends on formal legal, archaeological, and host nation approval. The next constraint is legal jurisdiction. The submerged aircraft represents sovereign property resting within the territorial waters of a foreign nation. Managing this boundary requires the operational mechanism of sovereign stewardship. Under United States law and Navy policy, a sunken United States military aircraft remains government property unless title has been formally abandoned or transferred. The United States Navy therefore retains ownership of Bureau number 1515. However, the host nation controls access to the water column and seabed where the aircraft rests. Access, documentation, and any extraction must therefore be coordinated through the Naval History and Heritage Command and the host government, under the permits and agreements each jurisdiction requires. This framework can impose substantial administrative delay before physical operations begin. Recovery teams cannot simply mobilize heavy lift equipment to the coordinates. They must establish the permissions, responsibilities, funding arrangements, conservation commitments, and custody procedures required before the artifact is disturbed. With the legal and jurisdictional boundaries resolved, the operation faces a severe engineering gap. The physical reality of the site dictates that possessing the legal right to lift the aircraft does not equal the technical capacity to do so safely. The entire value of the operation hinges on recovering an aircraft that retains its original shape and historical configuration. The recovery engineers therefore face a distinct trade-off between operational speed and artifact integrity. Any method that concentrates force through chains, narrow slings, or isolated lift points could tear the historical airframe apart. The decision is to use a conservation-led archaeological recovery model that distributes loads and controls movement around the wreck's actual condition, accepting greater planning time, equipment complexity, and handling risk to preserve the physical features that make it historically valuable. The next question is physical. Did the airframe retain enough structural continuity to survive extraction? On February 1, 1942, a severe operational limit forced a critical physical geometry test on the aircraft. Operating during the first United States offensive action of the Pacific War, the aircrew became disoriented as fuel dwindled and weather deteriorated. With the remaining fuel judged insufficient to regain the carrier, the pilot turned back toward Jaluit and carried out a deliberate ditching in the lagoon. The central problem of a water landing is managing the massive decelerative forces as a heavy aircraft strikes an incompressible fluid. The operational trade-off requires shedding speed fast enough to survive the impact, but slowly enough to prevent the forward momentum from tearing the airframe into disconnected fragments. Survey evidence is consistent with a controlled, nose-high ditching with the landing gear retracted and the flaps extended. That configuration reduced the risk of a violent nose-first impact. But the precise contribution of the low wing geometry cannot be proved from the wreck alone. The aircraft may have skipped or planed as it decelerated across the lagoon surface, but that motion is unconfirmed. What the surviving geometry does show is that the controlled ditching preserved much of the airframe as a connected structure. Following the ditching, the aircraft sank to the lagoon floor, establishing the environmental conditions that would dictate its long-term preservation. Divers later located the cohesive wreckage at a reported depth of approximately 120 to 125 feet. That depth forms a central environmental constraint for the forensic site. Its position farther inside the lagoon places it beyond the more exposed reef zones. The surrounding reef and the sheltered lagoon position reduce the force of breaking waves and storm-driven surface motion at the site. That protection limited repeated physical battering, although currents and seabed movement were not eliminated. At the same time, long-term immersion continued to drive chemical deterioration. Submerged in a relatively sheltered saltwater environment, the aircraft is subject to the mechanism of galvanic corrosion. The entire lagoon acts as an active electrolyte bath. An aircraft is not built from a single homogeneous material. It relies on various dissimilar metals in contact with one another. Steel bolts, brass fittings, and bronze components are mechanically joined to the primary aviation aluminum structure. When submerged in salt water, an electrical exchange occurs between these different metals. The less noble material, in this case the aluminum surrounding the steel fasteners, sacrifices itself and breaks down at a highly accelerated rate. The operational consequence of this galvanic corrosion is a hidden loss of load-bearing capacity. After more than 8 decades of electrolyte exposure, corrosion is visible around riveted seams, fasteners, and other dissimilar metal connections. Some joints may have lost substantial strength even where the skin still appears complete to a diver. Yet the damage is not uniform, and the surviving load paths cannot be judged from external appearance alone. This creates a severe evidence paradox for the recovery team. The deep water environment protected much of the aircraft's visual continuity, making it highly valuable, while concealed corrosion made its true handling strength uncertain. Any physical intervention, including direct rigidity testing, could trigger local damage or collapse. The recovery engineers cannot simply attach cables and pull to see if the structure holds. Sudden or concentrated tension may shear weakened joints, but the exact failure threshold remains unconfirmed. Before any lifting architecture can be designed, the engineering team must estimate which visible structures remain continuous and where serious deterioration is most likely. They need the most complete map available of geometry, damage, and uncertainty. How could recovery engineers reduce that uncertainty without imposing destructive force on the fragile aluminum? Following reports beginning in 1997 and the documented location of the wreck in 2002, the Recovery Coalition confronted the limits of standard underwater survey tools. Human observation and traditional dive cameras could record external geometry, but the established risk of destructive strength testing required the teams to proceed under non-intrusive archaeological and permitting constraints. To solve this measurement problem, the managing institutions implemented the mechanism of documentation restraint. Rather than rushing heavy recovery equipment to the lagoon, the team spent years documenting and monitoring the wreck before attempting physical extraction. The strategy traded operational speed for a progressively stronger evidence base, not absolute structural certainty. By enforcing this discipline, the project reduced unnecessary disturbance while building the best available model of the aircraft's visible condition. Between 2004 and 2023, the coalition conducted 7 reported archaeological expeditions to the site. The objective of these missions was not to move the aircraft, but to gather extensive external surface data and monitor visible change. The teams established a photogrammetric baseline using overlapping high-resolution imagery, later supplemented by subsea light detection and ranging. Together, those systems produced a precise three-dimensional record of the aircraft's visible geometry without applying lift loads to the compromised structure. The digital baseline strengthened the forensic case for identity and showed that the wings, central fuselage sections, and tail assembly largely maintained their historical geometric relationships. Crucially, the scans showed that the original radial engine remained associated with the forward airframe, but not securely mounted in its original position. Published surveys report broken engine mounts and a power plant and firewall assembly tilted downward and to starboard. That damaged concentration of mass became a major constraint for extraction planning. Knowing where that mass was located allowed the engineers to estimate the wreck's center of gravity and plan conservative support points. The calculation could not be exact because retained water, sediment, missing material, marine growth, and damaged attachments all affect the true mass distribution. The surveys, therefore, provided the measured geometry needed to design an external support system around the degraded airframe, rather than relying on its original structure alone. The greatest mechanical risk to any submerged artifact is not the ocean depth, but the boundary where the ocean ends. In 2026, a multi-agency coalition publicly launched the project to recover the aircraft. Cooperation among the host nation, the Naval History and Heritage Command, the Air Sea Heritage Foundation, and academic institutions moved the effort into active recovery planning, while final site-specific permissions and operational approvals remained part of the process. Utilizing the exact photogrammetric baseline established during prior surveys, the recovery engineers recognized that pulling the aircraft upward presented a severe structural hazard. The handling geometry had to be engineered perfectly to prevent the fragile artifact from disintegrating just inches from the surface. While resting on the seabed or moving steadily upward through the water column, the submerged airframe benefits from buoyant support. As more of the aircraft emerges, that support progressively decreases. The crane and support system must therefore assume a steadily increasing share of the load, rather than confronting a single instant when buoyancy disappears. Gravity then places increasing demand on the support system and on every point where the artifact contacts it. The raised load may therefore differ substantially from the aircraft's original dry weight. Waves, drainage, crane motion, and lift rate can add dynamic forces to that progressive transfer. At the interface, concentrated loads could crush corroded skin or distort the center section. The exact failure sequence would depend on sling width, padding, spreaders, support geometry, and the aircraft's hidden condition, requiring any direct band or point loading to be justified by detailed engineering analysis. To bypass this handling constraint, the engineering team will likely require a purpose-built external support system acting as a load-distributing skeleton around the aircraft. Public project material confirms recovery and rigging planning, but the final cradle design, material, assembly sequence, and diver tasking remain unconfirmed. Any approved system would have to support the forward engine area, wings, fuselage, and tail, while minimizing contact pressure and movement. Surface lifting cables could then attach to modern engineered lift points rather than directly to the historical aluminum, allowing broad supports to carry the increasing load across selected contact areas as the assembly crosses the air-water interface. This would reduce demand on weakened internal joints without eliminating contact pressure, differential movement, drainage loads, or hydrodynamic drag. This strategy cannot guarantee an undamaged lift, but it can reduce the remaining risk to a level the engineers and conservators judge acceptable. With those mechanical risks controlled as far as practicable, why was this deeper airframe selected instead of the shallower wreck nearby? When planning the recovery of an extinct aircraft type, the presence of multiple submerged candidates within the same geographic location forces a direct comparative evaluation. The Recovery Coalition investigating Jaluit Lagoon documented 2 Devastator wrecks in the same general area. The 2 candidates were Bureau number 1515 and the shallower Bureau number 0298. The record does not establish that recovering both was formally rejected as administratively or financially impossible. Instead, the coalition evaluated which aircraft offered the strongest combination of historical integrity, accessibility, and long-term preservation value. The first variable in the target selection matrix is operational access. The second Devastator rested on a shallow reef face. From a purely logistical standpoint, a shallower wreck presents a highly attractive target for marine operations. Shallower depths allow technical dive teams to utilize standard breathing gases, maximize their bottom time, and minimize complex decompression schedules. The rigid steel extraction cradle requires extensive manual assembly by divers working directly on the seabed. An easier dive profile drastically reduces the time and cost required to bolt that protective framework together. However, the second variable is the physical condition of the historical artifact. The environment that makes diving easier also exposes the wreck to stronger wave action, coral growth, and repeated disturbance. Bureau number 0298 has suffered serious damage. Its engine is detached, coral has colonized major areas, and one horizontal stabilizer separated between 2018 and 2023. Even so, substantial portions of the wings and fuselage remain. It is therefore better described as a damaged and increasingly vulnerable wreck than as a field of disconnected fragments. Those conditions make any full recovery more complex and help explain why in situ preservation remains the stated plan. Conversely, Bureau number 1515 occupies a significantly deeper operational zone inside the lagoon. Accessing this target imposes stricter limits on the recovery team. At approximately 120 feet, working time is sharply constrained, and longer or more demanding tasks may require technical gas planning, decompression, redundant support, and tightly controlled dive profiles. Those requirements increase logistical difficulty and operational risk, but mixed gas and mandatory decompression are not automatic on every dive solely because of depth. The ultimate operational trade-off therefore pits dive complexity against structural viability. Based on this comparative assessment, the multi-agency coalition selected Bureau number 1515 as the preferred recovery candidate. Bureau number 0298 is intended to remain protected in place as a cultural site. By accepting the harder dive profile and greater logistical constraints, the recovery team chose the artifact judged most likely to survive a carefully engineered recovery. The decision reflects the aircraft's relative continuity and preservation value rather than ease of access alone. Once successfully brought to the surface, what protocol will govern its preservation without erasing its submerged history? The moment the airframe is secured after recovery, the engineering problem fundamentally shifts from mechanical extraction to chemical preservation. The managing institutions face a strict operational trade-off between visual restoration and historical authenticity. The publicly stated intention is to stabilize and display the aircraft as found, retaining as much surviving historical fabric as possible, rather than rebuilding it to appear factory new. The exact limits on replacement material, fabricated supports, and structural intervention will be determined only after examination and testing by the conservation team. Exposure to oxygen and drying air can accelerate post-recovery deterioration, as chlorides remain trapped within the aircraft's mixed metal structure. If the airframe were placed on a transport deck and allowed to dry naturally in the sun, salts and corrosion products could expand, crack, and separate fragile metal layers. The rate would depend on alloy condition, chloride loading, temperature, humidity, and the condition of each component. Uncontrolled drying could therefore cause rapid and irreversible damage before the aircraft ever reached a museum. To prevent that deterioration, The conservation team from Texas A&M University must immediately begin a controlled stabilization program. The aircraft must remain wet during transfer and move promptly into a conservator-designed holding and desalination system. That system may use fresh water or an inhibited solution under controlled chemical conditions. Its final tank design, location, and solution chemistry will depend on the recovery platform and the condition of the airframe. The desalination process will not be rapid. It may require months or years of monitoring, fluid changes, and testing across different materials. Chloride levels, solution chemistry, corrosion activity, and the condition of each component must be tracked until conservators determine that drying can proceed safely. Only then can the team select any inhibitors, coatings, or other treatments appropriate to the aircraft's aluminum, steel, copper alloys, and remaining composite materials. The final treatment must be based on testing rather than a single generic chemical applied to the entire airframe. Metal lost to the lagoon will not automatically be replaced. The aircraft may be unable to support itself on its original landing gear, but that conclusion cannot be confirmed until laboratory assessment after recovery. Therefore, a purpose-built museum support structure will likely be required. Its final location, visibility, and construction will depend on the condition revealed after desalination and stabilization, with the goal of carrying the load without disguising or damaging the surviving airframe. If recovery and stabilization succeed, Bureau number 1515 is intended for permanent public exhibition at the future National Museum of the United States Navy. The aircraft would retain the physical record of its 1942 forced water landing and more than 8 decades beneath approximately 120 feet of water, stabilized for long-term preservation under continuing environmental control, inspection, and care.